Hi, this is Umut Kocasar and I am going to present ranking style, a ranking-based approach to find interpretable directions. This is a joint work with Kerem Zaman, Mert Tiftikçi, Enis Simsar and Pınar Yanardağ from Boğaziçi University and Technical University of Munich. Our method is capable of finding relevant and editable keywords by using a list of text prompts. Those keywords can be used to manipulate images from various domains. Our main motivation is to find interpretable directions corresponding to specific keywords in StyleGAN by using a novel ranking-based approach. Also, we propose a clip-guided beam search decoding strategy to generate a list of keywords that can be used to perform domain-specific edits. It is particularly useful for scenarios where domain knowledge is limited to generate reasonable text prompts such as fashion. The first part of our method is keyword ranking. By using a list of keywords, we rank them accordingly by considering their relevance and editability values. We calculate those values for each channel keyword pair and assign each channel to a specific keyword with the highest scores. The final score is calculated as the combination of the relevance and editability scores. Relevance score measures how much similar images and keywords are. The keywords should be related to the generated images. We calculate it as the clip embedding similarity between the image and the keyword. S is the style code that generates the original input images. G is the pre-trained StyleGAN2 generator. T is the text prompt. S clip is the cosine similarity between clip embeddings. Editability score measures how much suitable the keyword is to edit generated images. It is calculated as the similarity increase with the text prompt divided by the magnitude of the change. The magnitude of the change is measured as the L2 norm of clip embedding difference. Alpha is the degree of perturbation. Clip is the model to produce embeddings for images and text, and L2 is the L2 norm. Those scores are calculated for each channel keyword pair. We find the keyword for each channel and we rank pairs according to their score differences between channel first keyword pair and channel J keyword pair. J is chosen as 10 in our case. This takes disentanglement into account. So the channel should represent a specific word but should not represent other words. Final scores to rank them are calculated as the multiplication of relevance and editability scores. Here we aim to generate a set of phrases suitable for domain-specific edits. In order to do this, we intercept beam decoding by altering likelihood scores of top K candidate tokens with clip similarity scores between images from the target domain and the generated text so far. Maximum length of the generated sequence, size of the image set, control parameter eta, chosen prefix text, and engram sizes are hyperparameters to be tuned. Initially, we select prefix text and maximum length along with domain-related images for free generation. We have seen in our experiments that domain-related prefix text such as dress width helps further focus free generation to target domain. We store each beam state in a corpus so that the diversity is increased. We then apply TF-IDF to the generated corpus, where text generated for each image is treated as if they were documents, and engrams extracted from the term them as terms. We select phrases with highest TF-IDF scores as a set of domain-specific phrases suitable to be used for editing. This final step is applied to extract phrases that could edit the target domain in general rather than specific image or feature related to the sample at hand. Also, it helps eliminating nonsense text generated by the model. Here are the edits on FFHQ dataset. The leftmost column represents the original image. We compared our method with StyleClip and StyleMC methods. These are the top-ranked keywords among produced set of keywords. We see that our method makes successful edits such as red hair showing, green background, mouth open, red lipstick, and orange. The figure shows that the keywords and edits are highly related to each other. Also, when compared to other methods, our technique produces comparable results. Also, we tried our method with different datasets. One of them is fashion. As we can see, there are successful edits such as orange, lime brownish, and black cotton dress. Another dataset we tried our method is AFHQ cats. As can be seen, the keywords are very diverse from each other and make the desired manipulation. It changes fur color, skin color, eye color, noise type, and eyes. Also, when we look at the results on AFHQ docs, we see similar successful edits. The keywords and effects are overlapped and diverse. They change the color and mouth. And the edits for AFHQ wild. We see that it finds the keyword changing species such as tiger Tibetan. Also, we see the change in ears, eyes, and color. Finally, another dataset, Al-Sunkar. We see that the color change keywords such as black tires and brown paint, and the type change keywords such as mini and mini Ford. As a conclusion, we present a novel rank-based approach to image manipulation by finding interpretable directions in StyleGAN. Previous work requires prompt engineering to perform text-based image manipulation, which makes it inefficient for some use cases. But our method is able to discover interpretable edits among a large number of domain-specific keywords. We solve the problem of collecting large number of keywords for a specific domain by introducing a clip-guided beam search strategy. Also, we compared our methods with other methods in terms of disentanglement and semantically meaningful changes and obtained favorable results. And thank you for listening.